Alright you guys, so this is the second section of our lab. The first section, what we did was we put together a raw data table as well as a graph. So we should already have that finished. So I'm going to show you what the next steps of this lab are going to be. Now this isn't going to be a full lab write-up, it's just going to be components of what would be a full lab write-up. So you notice that I put my name on this document, and then the first thing we're usually going to write down is a problem. So this one, fix a spelling mistake. The problem is, to what extent can an inclined airtable be used to calculate the acceleration due to gravity at the Earth's surface? This is really what our problem is we want to determine what g is. Hopefully we get a value close to 9.81, but this will be an experimental value. We may not get exactly that because we may have had some experimental error. Now, after you state your problem, the next thing we state is background information. Now, for this one, the first thing that I want you to do is write a free body diagram, or draw a free body diagram. Okay, I'm not going to fully draw this one out because I want your guys' to look a little bit different than mine does. Now I suggest that you can go in and you can just use some of the shapes here, make a nice free body diagram. You'll have all your arrows for vectors, and you guys can go ahead and do that for the air puck traveling down the table. Okay, so the next thing that we're going to do in our free body, or in our background information, I will show you guys, and it's going to be the equations that we're going to use to derive acceleration due to gravity. So the reason I'm going to show you this is I want to show you guys how to write some equations in Word. Now you'll notice over here with your version of Word, likely you'll have something that says equation, and you can use this, you guys. It's something called math type. Okay, but for me personally, it's not my preferred way of typing in equations, so I'll show you my way. So instead of going to that equation, I'm going to go to Insert, I'm going to go to Object, and you should find something in here called Microsoft Equation 3.0. Okay? So what you'll see is a little box pops up. And this may look intimidating at first, you guys, but it's going to be really useful for us. So you'll have already drawn your free body diagram, and now we're going to write in some equations. So the first thing I want to write in is the sum of the forces in the x direction is equal to mass times acceleration. So I'm going to click on this button right here, and we're going to see this little sum. So I'm going to click on that, and then we can just fill in the rest of this. Now I want to subscript something, so if you see this button right here, I can click on a subscript and it will subscript this. Now, if I want to get out of subscript, what I want to do is I want to hit the right arrow key. If I don't hit the right arrow key, I'll just keep on typing in subscript. So I hit the right arrow key, it gets me out of that. Now I can simply just finish writing my equation. So if I don't want to go back into equation editor, what I can do is I can just Control C, Control V, and another version of this will show up. So now when I double click on it, I can just edit this version right here. So now what I'm going to say is, well, the sum of the forces in the x direction is equal to the force due to gravity in the x direction. Subscript down there. Now you guys will notice that I've put this into column format so that it looks really nice. It's going to be very clean for us to look at. Okay, so now I'm going to equate these two things together. So once again, I'm just going to hit Control V, and I'm going to type in FGX is equal to MA. Okay, from our free body diagram, we'll know that FGX is equal to sine theta times FG. So if I copy and then paste down here, I can just say that FG times. And if I want to actually put in a multiplication symbol, what I can do is I can go to these operators and I can put in a little dot. Theta is the symbol. It'll be over here. And actually, this formula right here, instead of putting in FG, I'm just going to put in M times G. What we'll notice is our masses will cancel out, and I'm left with G sine theta is equal to A. So let's copy, paste, take out these masses, copy, paste, and I get that G is equal to A divided by sine theta. Now if I want to do a divided by, I can just highlight this A, and then I'm going to click on this button right here and go divided by sine theta. And this is an equation that I'm going to use to calculate out G. I already know what theta is for the free body diagram, or for our inclined air table. Our inclined air table has an angle of 3.5 degrees. So when you're doing your free body diagram, you would probably want to mention that the angle is 3.5 degrees, or just state that somewhere. Okay, so we know what theta is because we actually made that measurement when we assigned the puck, or at least I did with a protractor. And now we need to figure out what the acceleration is. So going back, we had this table here. We'll move this up. And we had a figure. I had you guys do a trend line for this. And this is going to be very important because we're going to use this trend line to try and determine what that acceleration is. Okay, so this is a function of this parabola that represents our data, and we notice that this represents my data very, very well. And I think a lot of your guys, as your trend line, represented your data very, very well. So now what we're going to do is we're going to show how we're going to calculate acceleration due to gravity. Okay, so an equation that we're going to use, you guys, is off of our formula sheet. And let's write in another equation. So I'll just hit Control V just so I have equation editor open. And our equation is going to be that D, and if we want to use our subscript x's, we can. So dx is equal to Vix Do you know what? I think I'm just going to make this a little bit easier, and I'm not going to put in the x's, just so that it'll look nicer with the subscripts. So from kinematics, we know that d is equal to VIT plus 1/2 AT squared. Now we've done the subscript. If we want to do a superscript, we just click on this button right here. And there we go. So in our graph, our total distance is our y variable, and our total time is our x variable. So what you'll notice is we have a y here, and we have an x, and we have an x. So if I look at this equation right here, you guys, I have d is equal to VIT plus 1/2 AT squared. So you'll notice this value up here, this 252, well, that must be 1/2 the acceleration. This value right here, 59, well, that must be the initial velocity, because that's the value before this x. This minus 1.1445, we can totally ignore that. That in a perfect world should be 0. Okay, so we have this equation right here. Okay, so what we can do is we can do a bit of an explanation here. So we can say, since in the figure the y variable is distance and the x variable time from the quadratic regression done by Excel, it can be seen that and I'm just going to put this over here. So what I'm going to state here is that 252.13, and if I think about what the units should be here, I have millimeters up here and I have seconds here. So I'm going to put in those units. So once again, I'm going to use equation editor because it makes my units look the nicest. So I'm going to put in 252.13, and my units for this are millimeters per second. Is equal to 1/2 the acceleration. Oops. So let's go back into equation editor to do this whole equation. And if you guys ever want to do a space in equation editor, so you want to make some room for something, you have to hit Control Spacebar. So I'm going to do that just so I can show you. So I'm going to hit Control Spacebar a bunch of times, and then I'm going to put in a therefore symbol. And then what I can do is I'm just going to write in, well, if 252 millimeters is 1/2 the acceleration, therefore, and then we can put in another equation, the acceleration is equal to, well, it would be 252 times 2, 504.26. And then if I want some units here, I can always just copy and paste over these units. There we go. So now what we have, you guys, is we have an acceleration as well as we have an equation to calculate for g. So we know the acceleration now. We know the sine theta, so we can figure out what g is. Okay. So that's a little bit complicated, but hopefully you guys could figure out what that means. So the next thing that we're going to do is maybe let's instead of titling this calculation of acceleration due to gravity, let's just say calculation of acceleration because what we're actually doing there is we're calculating that acceleration of the puck down an inclined table. Now what we're doing is we're actually calculating acceleration due to gravity. Okay, so we have our equation from before, so we can grab that. Let's just Control C, Control V down here, and we can input in some values here. Now I'm going to get acceleration due to gravity in millimeters per second. Ooh, these should actually be millimeters per second squared, because that's what accelerations are. So this will be squared. This also will be squared. Okay. So let's actually put in our values here. So once again, Control C, Control V, my acceleration, and I can just grab this value right here. I try and do as much copying and pasting as I can, you guys, to save ourselves some time. And this will be sine of 3.5 degrees. Actually, I should show you how we can do the brackets here. So 3.5, I'm going to subscript, so I can put in a degrees symbol. And then what I'm going to do here is I'm just going to put this into brackets. So if I want to do any brackets, I click on this button here. So this is a bit of a weird number here. So what I want to do is I want to convert it into base units. So if we convert this guy into base units, we're probably going to have to go to another page here, you guys. It's not ideal to start another page, but because this is only going to be page 4, if you double side it, you'll be able to fit this onto 2 sheets of paper. So this is going to be our final value here. I am going to put in that multiplication symbol. And now that we got this big guy right here, let's just put in equals. And what we're just essentially doing is we're dividing this by 1,000. So what we get is we get 8.26 meters per second squared. Perfect. So we're going to get an acceleration due to gravity being equal to 8.26 meters per second squared, and maybe we just want to state that in a box here. So we'll put in our final equation, you guys. Beautiful. And I think I just want to put a little box around this. Okay, now typically what we're going to do at the end of this is we're going to do a percent error calculation. So how we're going to do this percent error calculation is I'll actually show you math type for this one. So if we go to insert equation, it just works a little bit better than equation editor. So we're going to use this. So it's going to be the accepted value minus the experimental value. And then in this case, we're going to see this fraction, put in a fraction, and that'll be divided by the accepted value. Going back into our equation editor, so let's just grab one of these. Now our accepted value, clearly for acceleration due to gravity, is 9.81 meters per second squared. The experimental value I got, it'll be different from what you get, was 8.26. And once again, I can always just grab onto those units. And that's divided by our accepted value. And if I quickly do that calculation, I get a 15.8% error. So this is pretty much everything that we need to do for the next part of this lab. So hopefully you guys can put all this together. Once again, if you have any questions, just ask in class. Thanks.